Thank you very much. I was told I have to stay in this little box here, so that's going to be a bit of a challenge because sometimes I like to point out things on the screen, but I'll do my best. My name is Nick van der Giezen, and I'm going to tell you about a project that is just taking off in Africa. And it has a complicated name, maybe, Trans-African Hydrometeorological Observatory. And you may wonder, why do you take such a horrible name? Well, we like the acronym, the people involved. It's just not me, it's also some other people I will come about later on. And the acronym spells almost the name of the guy who was our promoter. And we did our PhD work with him, and that's why we like the acronym, and he did a lot of work in Africa. That's why we have this somewhat longish name, but easy to remember in the end. This is the outline of my talk, as to tell you a little bit about why we're doing this, what we're trying to do actually. We'll talk about some design issues in what we're trying to do, how we hope to run this project, and then in the end also going to talk a lot about education. And I hope that at that point, I mean, I'll try and be as brief as possible so we have some time to get some feedback, because we think high schools have an important role to play in this project, and I hope to solicit some feedback and some comments from you, so you can actually, and it's not just me telling you stuff, but I hope also to take more home than I'm giving to you. It's a bit selfish, but it's for a good goal. I will show you. It's about water in Africa. What is? Let me start out with this map. These are the World Meteorological Organization has a number of weather stations, about 5,000 in the whole Earth, on the whole Earth. And all the stations you see here have one dot. And the blue ones, they tend to report 90 to 100% of the time. The green ones, 45 to 90%, the yellow one, less than 45%, and the red ones are silent stations. And it's quite obvious that outside some few places in Africa, Northern Africa, Southern Africa, Africa is really an empty continent when it comes to weather stations. We don't know much about Africa. And in the meantime, we keep talking about, well, climate change impact, droughts, floods, all these things, and we don't, you know, with this continent where we're actually looking forward for increased food production. You know, it's going to be the breadbasket of the world in the next 30 days, 30 years. 30 days, that would be nice. 30 years, and we don't know. We don't know what is going on there. We have not been seriously measuring there. And of course you can say, well, then we're a bit late, but you know, we think that we should start measuring there to see what's happening. Where are you going to do what, etc. But let me start with this one. So worldwide, 5,000 stations are communicating more or less on a daily basis with the World Meteorological Observatory. I think about 1% of those are in Africa, but let's say we have 5,000. If we look at the rain gauges, in the first lecture this morning you saw some of these rain gauges. It's very easy to measure, we say. It's like, so if we take the surface area of all these rain gauges that are reporting to WMO, so how many soccer fields do you think we can cover with that? Yeah, if we put them all together, I mean, any idea? One? Half? Anybody for 10? This is what we can cover. Yeah, so it's a very small part, and if you take only 1% of that, you're probably just talking about, you know, this center dot in the middle where they start the game. So in Africa, we really, you know, worldwide we don't know much, but in Africa, we really are short of data, I would say. And it's interesting that we're looking then, you know, with this little bit of data, we're looking for trends and changes in extremes and things like that. Of course, there's other things, and you know, there's some it's not as simple as this, but you can see that it's not an easy thing that we're trying to do here when we're measuring climate signals. The idea of this project now that I'm talking about, this TAMO project, is we want to leapfrog. We just want to say, okay, you can of course try and follow the historical path that other parts of the world have taken, but no, let's just leapfrog. Let's jump to the next generation of weather stations and of meteorological stations and hydrological stations. So in 5 years' time, Africa, the map should look like this. We have 20,000 stations in Africa. We're going to do it completely differently there than anywhere else in the world. And can it be done? Well, I don't know. We'll hope so. But it's definitely true that some of these new technologies are moving faster in Africa than they are, for example, in the developed world. So there's definitely hope that this is a possibility. For example, paying people with cell phones is a very common thing in Africa. It's a very practical thing, and here we still have to look for the coins or for the little cards and stuff like that, and there things are happening faster. So it is definitely possible that a new technology brought out from Africa could revolutionize in a way the way we start measuring our climate. 20,000 stations, is that enough? Should you have more? Should you have less? Why 20,000? Well, this is sort of in the end, what we try to get at. We are focusing here on the ground observations, but the ground observations by themselves are not sufficient. You also need models, big models. We have, of course, a lot of big models, especially meteorologists. Hydrologists are still a little bit behind on that. We don't have a serious global hydrological model yet. At least not in operational sense like the meteorologists do. And we need remote sensing. The first lecture you showed today, it's a sea of data. And you definitely need that. We don't want to say, forget about it. No, you need those remote sensing data very much because you need this consistent global coverage. But we still think that you can do an awful lot if you have some smart ground observations. So, just to show you the interesting thing that you can do with we already saw some movies before. This is a movie of the so-called NDVI. This is just the greenness of the vegetation, if you want, in 10-day steps for about 9 years. And you can just see this whole continent breathing. And you can, at this moment, we're not really using the information that's in here. At least not within hydrology, and even not so much in meteorology. In an indirect way, maybe. But you can see an awful lot of detail. For starters, of course, this large breathing, if you want, of the continent, where the monsoon comes and the monsoon goes. But you see other very interesting details as well. For example, this area here, the Angolan highlands, they are sort of like these water towers. Africa has about 3 or 4 water towers where a lot of rain is falling and it's feeding really these bigger rivers. So Angola is one, the Ethiopian highlands, the Futu Jalon here, they're feeding, this feeds the Niger, this feeds the Nile. These are really, places that are greener and that's sort of collecting a lot of water. But even smaller details. For example, this one is the internal delta of the Niger River. So it's smaller, but it stays green. It's sort of like a big swamp, not as big as the Soot, which you can see here as well. So when the dry season starts, you can see it stays greener a little bit. So there's an awful lot of detail you can see, and we should be using this. But you keep guessing, it's like, what is it exactly? And these large features, of course, you can figure out. But to really understand, okay, was it a disease? Why is it not green this year? Was it a disease? Was it a lack of rain? Was it over-exploitation of resources? What was it? You still need some ground measurements. So that's why we focus in this project on ground measurements. And we want to have 3 things actually in a way. We want to have a special design of these stations. We want to have a special way of operating the whole system. It's not going to be easy, 20,000 stations, how are we going to do that? And we think that education has a role to play, both in terms of operating the system, because we want to run these stations at schools. But on the other hand, we also would like to, we think the project can have an extra output by teaching children to observe their environment, showing them that their environment, they are part of a larger system, and that a larger system is sort of affecting their direct environment. And that's, I think, is an important thing also, that the children go out and measure things, especially in Africa. I'm not sure, how many of you have been to Africa in countryside? I mean, I'm not talking about the Canary Islands, but who has been to So a handful of people, you know, so if you have seen schools there, you know, maybe they have a thermometer, but, you know, the kids are not allowed to touch them because, well, there's only one thermometer, so the teacher would be probably just drawing a thermometer on the blackboard and saying, hey, this is it. So really touching something, measuring things, is not really yet part of the curriculum. And in order to have good environmental scientists 10 years from now, 20 years from now, it might be helpful to have an improved environmental curriculum in the schools. So the design, well, this is not, I mean, I showed this once, and since then people say, oh, this is the new station. Well, I don't know, I just, for the first time in my life, I tried Google SketchUp, and this came out. Then I imagined that it would be about this high, but other people imagined it would be, you know, extremely high, like tree high or something like that, and other people would think it was about the size of a golf pin, you know, these little pins they have, so we don't know yet. Probably it will be about a little bit bigger, but it has to be, the whole point is that it should be one piece and it should not have any moving parts. I'll come back to the design criteria a little bit later. And we want to measure things. We want to measure standard meteorological variables, rainfall, shortwave radiation, longwave radiation, wind speed, temperature, relative humidity, standard things. Maybe also some less standard things like soil temperature, soil moisture. We might want to have a GPS in there, just to know what's happening with your station, where it is. That there can be no question there. Also, the GPS contains some information about the atmospheric buildup and stuff like that. Maybe we can have also very new kinds of sensors. And we're definitely working on that. Now, in order to have 20,000, it can, you know, a normal meteor station now, if you buy a professional meteor station, it costs about 5,000 to 20,000 euros. So that becomes a little bit inhibitive if you want to have many of them. It's also a little bit difficult to say, okay, you go to a village and you say, here, wonderful thing, here's $10,000 worth of equipment, when maybe, you know, the cash income of the whole village is 10,000. So that's also a bit strange. So for several reasons, we want to keep the cost low. Also to have it, you know, if something does break down in the end, okay, it's a pity, but, you know, here's another one, and, you know, let's hope they don't break all at the same time. So we're thinking, and when we started out, we were thinking $200 per station. So 20,000 stations would be $4 million. It's not nothing, but it's overseeable. In the meantime, prices are going up and crisis is coming. So now we are at 300 euros, but still, we are hopeful that we get it for a decent price. 20,000 stations, by the way, means that every 35 kilometers, you know, if you work on a grid of 35 kilometers, every grid point you have one station. Quite ambitious. Now, how are we going to build, you know, how can it be that you know, there must be a reason why these meteor stations cost 10,000 euros. And why do we think we can make them for 200 or 300? It's like, well, these things have been moving lately, or last 20 years, let's say, especially in terms of sensors. You can have, you know, everything these days is filled with sensors. Everybody who has a smartphone, there's an accelerometer in there, there's a compass in there, there's a microphone, a light sensor usually, a proximity sensor, whatever. Anyway, it's full, it's loaded with sensors. It has radios in it, ways of communicating, and it costs 200 euros. So it can be done. Cars are full with sensors, household items are full with sensors. And so the idea is just to pick out these things. If you have to start developing these from scratch, it will be a very costly pathway, and we would not be able to do it. But there are existing ones that you can use. One old favorite is, because it has this futuristic name, the Zytem TN9. And this is what it looks like, and it measures long-wave radiation. So the radiation associated with temperature. So about 300 Kelvin or about 30 Celsius, you know, everything radiates at a certain, on Earth, has more, you know, radiates at about this longer wavelength, this infrared wavelength, and this measures it, and it comes out of thermometers, you know, these little point and shoot thermometers. And when you look at it, it's interesting. It has a large thermal mass to make sure that it doesn't go up and down all the time. It has some electronics, and it has then a thermal pile, and a little screen that makes sure that only long wave radiation goes in. And then you can buy, this costs about 10 euros. And the whole thing, and it has its calibration data on the chip and everything, very nice instrument. And then the official one measuring, when you look at a design, it has the same design as this thing, except it's a bit bigger. But it also has this large thermal mass, it has a thermal pile, it has this little screen. It's exactly the same principles. Except that in that case, usually the calibration parameters are not on the chip, but they're on a piece of paper that you always lose when you need it. But otherwise, exactly the same thing. And that one costs about 2,000 euros. So with this factor 200, if we find enough of these sensors, we might be able to build ourselves a very smart station for little money. Now, the principle, the design, I mean, as a bit of a, we get a lot of fun out of designing things, thinking of smarter ways of making these things. And of course, number one, it has to be robust. We also don't want to have any moving parts. Anything that moves, dust will come into it, it will stop moving. Especially weather, wind measurement things and stuff like that. They're very difficult, very easy to break and easy to go down. We also don't want any open cavities. Why not? Well, everything we put out in Africa, which has a nice open cavity, the insects agree. This is a very nice open cavity, and in no time we have bees, wasps, whatever, anything building their nests in there. This is on a temperature sensor in one of these nice little shaded things and stuff like that. It's not so easy because we know that if you want to measure air temperature, you want shading, for example. The WMO guidelines say you need shaded measurements because otherwise you're just measuring the radiation from the sun. So are there ways around it? Yes, there are ways around it, but you have to do some other tricks. It has to be cheap. And ideally, because they will be kind of autonomous and they will be kind of out there, they have to be self-calibrating. So maybe you have more than one sensor or two sensors measuring similar parameters, but you can cross-calibrate. You also will compare it, you need some smart algorithms to compare it with your satellite data, with any information you can get your hands on, making sure it's still working. So these are the principles we're trying to follow. Now let's start with the first parameter, rainfall. The first guest said that the first speaker said it's very easy to do. And I was thinking, okay, probably someone who works for the space agency and not someone who works on the ground, because it's not so easy as you might think. Of course, you can put out a bucket and at the end of the rainfall, at the end of the day, what's in the bucket is what your rainfall is. But if you would put out maybe 10 of these things, you would find an awful lot of spatial variability. So it's already quite a tricky thing. And then, of course, they have cavities, they have funnels, they have, often, when you want to know something more about rainfall, like the rainfall intensity, which is very interesting for runoff and erosion studies and things like that. You often have a funnel with a little tipping bucket under it. Now, that's a moving part, so it's a big no-no. So it's not so easy to measure rainfall in a careful way, in a smart way, without any moving parts or cavities. So what is out there in the market? Well, there's something out there that they call dysdrometers. Are there any Greek people here? Yeah? So dysdro is? What does dysdro mean?
It's not easy.
That's not easy. Okay, no, is it not? Doesn't it mean drop, or is it Latin? Distro. No. Uh-oh. So I better go back to high school and beat up my Greek teacher, because I thought that was meant. Distros means drop, but apparently not. Okay. Drop. Anyway, the way we use it, this dysdrometer. Stagona. So it should have been stagonometer. Sorry about that. But meteorologists call it dysdrometer, and it means a drop meter. So it measures all the drops. That when it rains, it measures the size of each single drop. How many drops? How big are they? What is the volume? And there's different principles for that. But the big ones, especially these ones, the better ones, the video ones, they set you back about 10,000 euros. That's a lot of money. Now, not every weather station has one of these, of course. You don't always need it. Sometimes you just want the total rainfall or some other ways of measuring intensity. But we thought it would be very nice to measure these drops, again, for maybe erosion studies. but also in concurrence with these satellites that measure reflectivity. And if you then know something about the drop sizes, are these big drops or small drops, if you can relate that to what the satellite sees, you get much better satellite products. So we asked the student, say, come up with something. It shouldn't, you know, these design principles, blah, blah, blah. He tried like 5 or 6 or I don't know, maybe even more different ways of measuring rainfall. And he came up with this one. After all these things he tested, this was the best thing he could find. And it's one of these things, and we probably have about 5 or so in this room. They're in these alarms, and it's a piezo buzzer. Okay. And so normally it's in many places you can find it. So basically what it is, it's a piezoelectric material. If you put a tension on it, it will move a little bit. So if you put a tone on it, it will start beeping. And that's why they're all in these things. They used to also be in these cards. When you open them, you get a little song. So they're very cheap. This is about the size. You can also have them slightly bigger. And this is about the price. So we were very happy with it. Because it also works the other way around. If you bend it a little bit, it gives you a little voltage. So when a drop falls on it, you get this nice sound, and that you can measure. And so of all the things that we tried, this was the best thing. And it has no seriously moving parts. Of course, it vibrates a bit, but it's not, it's not moving in a normal sense. And this is what one of his first signals was. It's very simple. He was a very practical guy, even though he was a physicist. Yeah, they're not always very practical. They're very smart always, but they're not always very practical. And he was very practical because he took the thing, glued it on, and put it just in his computer and used a sound card. And this was his first signal. And you already see it varies. Nothing's happening, just a bit of noise, and then chuck, a drop falls, and you get this nice dampened sync function. And yeah, he did of course some more work on it. This was just the raw element, and just trying it, and then you get a very good signal. But you cannot put it out there because then, yeah, it would get dirty and it would rust, and it's not made to be outdoor like this. So you have to put it in some housing and stuff like this. And we did this. By the way, the whole precipitation question, it's not such an easy question. So when a drop starts falling in a cloud. Of course, let's say it starts falling, it accelerates, but while it's going faster, also the air resistance against the drop is also increasing, because that sort of depends on the speed. So at one point, the resistive force and the gravity forces are in equilibrium. And it happens quite fast, actually. Even for big drops, after about 10, 15 meters, it has reached the final or terminal velocity. So for each drop size, it is associated with one terminal velocity. So that means that the energy or the impulse of the drop can always be correlated with the size of the drop, and that's very nice. That's why these disdrometers work, actually. Now that would be very easy, very nice if all these drops would just be nicely falling like this, but they're not. They're always colliding. For example, the bigger ones will fall faster, so they will catch up with smaller ones. They get even bigger, they go faster, and they catch up with more smaller ones. So they keep growing. This is a typical, also this is not just different drop sizes, but it's also the way these drops tend to evolve in a rain when they're falling down. It's a very complicated process. I had no idea when we started this. And we always, when we draw a drop, we draw this drop that is hanging from a faucet, with the tip on top. Actually, that's not what they look like. In reality, they're sort of these, when they get bigger. I mean, in the beginning, they're nice little spheres, but then you see they become a bit flat because they're going against this resistance. The air is pushing up, and they're getting bigger and bigger. If they get a little bit bigger than this, actually the air will come in here, becomes a bubble, and it bursts again. And then all of a sudden, instead of having one big drop, we have a lot of small drops, and then a larger one comes by, picks up the one, and that happens 4, 5, 6 maybe, I don't know how many times before the drops are at the end, are at the surface of the Earth. So it's a whole science. There was even a Nature paper, I think, on some nice experiments and people doing that. It's one of these two. I'm not sure if it's this one or if it's this one. So it's quite a. You think, okay, rain, drops falling. I mean, we know all that. It's like, no, when you start looking at it, even the physics are not completely understood. And also how then a drop in the end splashes on a surface is also, well, apparently still subject of study. So, given that rainfall is not as easy, I hope you have convinced you of that as you may think, what can we do to measure it? So, well, Koen, he went on and he measured, he now made a nice little cover on it. He gets a slightly less big signal, but he still gets a very nice signal. And like I said, this is the impulse. So he just looks at the amount of energy in this signal. Just if this is the x, and then if you square that and you sum that, then you get the energy in the signal, and that's what he then uses as a measure of the drop size. And lo and behold, this is what he finds when we go into the lab then, and we start dripping from about 15 meters down on these little disdrometers. These are log scales, so this is about a 1 millimeter, and this is about 2 millimeters, 3, 4, 5 millimeters. So he goes from 1 to 5 millimeters, and this is what the signal he gets also on a log scale. So he finds what they call a power law, but it's a very nice fit. So now we have this simple sensor, a very good correlation with the signal. So we should be able to do something now. And now we are able to back out for each drop that falls what the size was. Because this is what we measure. If we measure this signal, then the drop must have been this size. Now there's still quite some noise around it. Yeah.
This supposes that each drop is separated from the next one for some minimum time.
Yeah.
So it's not for heavy rain.
Actually, the remark here is like, okay, what happens if you get tuck, 2 drops right after each other for heavy rain, for example, and that can happen, and then your system is, of course, your signal is a bit messed up. What you can do, however, and so the statistics are fairly well understood. You can imagine if you have a very large disdrometer, that will happen a lot. And it's actually the ringing time is fairly short. So it's like we're talking milliseconds here. If you have a very small one, this may never happen. But if you have a very small one, you also miss a lot of drops. So you can then optimize for how big do you want your disdrometer to be to measure a certain rainfall intensity, because every rainfall intensity will have its ideal size, if you want, and we're doing that, and for now we're especially interested in the heavier, these nice tropical rainfalls. So and actually it also functions a little bit better on that side of the spectrum. So that's why we have relatively small ones, and it's nicely working. But it's a design, maybe in the end we end up with 2, one small one and one big one, if we can do that cost effectively. Well, that's one sensor down, but there's many to go, and even this one. We started a little spin-off company from the university, and actually, although it was designed with Africa in mind, turns out it also has very nice applications in cities and urban places and whatnot. We're developing this sensor a little bit further, but it's a lot of work. Yeah, it's a lot of work. It's one thing to have a nice idea, but it's quite a different thing to have something that works out there, is robust. It's really foolproof in a way. So if we keep doing that as a small team, we're now about 4 people in a team that are sort of like, spending a lot of time on it. It's John Selker at Oregon State University, Mark Andrini at the University of Nevada in Lincoln, and Rolf Hutt, one of my PhD students. So it's a small team, and we're very dedicated, but we cannot do this. It would take way too much time. And by, maybe we have a design by 2020 then, and we retire and whatnot before it's all there. So we are a bit in a hurry. So we're looking for partners. We're looking for academic partners. That's what we're doing here at EGU. We're really asking, so it's like, okay, if you have any ideas, if you want to be part of this, please come, because we need more hands, we need more brains, especially. It's a very complicated project, but we're also looking at businesses. For example, Decagon is a small company. They make very robust stations already. They share a lot of the ideas. They're very dedicated to agriculture. Of course, they have to earn. They have to make a profit, but they are very much dedicated to also get better agriculture, especially in places like Africa. So it's a very nice company we're working with, but you also need money. Well, and we are a bit naive, so we think if you have a big company, they have a lot of money, And that's true, but they, you know, they didn't get back big by giving away the money. But at least we are having some good discussions lately with IBM and with Intel. And you know, all these companies, they understand that all this censoring, all this information, this big data, you know, they, at one point, one way or the other, they're going to be in there, or they have to be in there, and they're going to earn money by analyzing this data, providing services based on those data. Plus, of course, they also, you know, it's a very nice project. If you improve agriculture in Africa, you might want to be, you know, part of it, and you know, so they want to be yeah, part of a project like this. So we're hoping that also these larger projects, at least these ones, are now quite serious about cooperating with us. Still, we just need more brains, especially students, we think. Now, we also need a business case. We want to, you know, you cannot cook a meal anymore these days without first designing a business case. We all need business cases. And this is what we sort of come up with. So it's like, okay, if we have 20,000, it would cost 4 million to do. Maybe the whole design and the first prototype, 1 million. An educational package, maybe 1 million, probably a little bit more. The whole rollout, you have to go there, you have to educate people, you have to set up a system. All these things maybe you know, would probably be the largest cost. We need some computation. You have to make sense of these data. You can, you know, just the raw data is nice, but you know, in order to do more with it, you need some extra stuff. So we think 18 million. It's a lot of money. Maybe it will double. I don't know. But how much do you think one satellite costs? You know, probably. A good satellite.
Well, depends, of course, on the length of the operation, so on. Just a launch or the operations? Or?
Let's say ESMOS.
Well, of course, we are talking about hundreds of millions,
yeah. So it costs about between 200 and 300, you know, then you have everything, including the launch. So yes, it's a lot, but if it adds, you know, if this would double the value of one satellite, I'm not saying, you know, or maybe many, or several things, it might be worthwhile. So it's a large amount of money, but it's not a ridiculous large amount of money. Then, of course, we have running costs, which we estimate at 2 million a year. And somehow this system has to earn its keep. We cannot just say, okay, we just keep giving 2 million a year and then we get a lot of data. So somehow we have to think of a way to earn some money with this system to keep it up. So I'm not a businessman, but someone has to think it up. Yeah, so we need 2 million a year, and for that we need this business case. I think we think it has a lot of value. For example, local food aid. Now, what happens when there's hunger, especially in Africa? They get corn or whatever from the United States or wherever, or France or Australia, and they bring it there and they dump it on the market. And that's usually not such a wonderful idea. Yeah, partially it is for the immediate needs. Yeah, it also destroys the market for the local farmers. They have to compete with food that's basically free. How are they going to do that? So what's smarter is to say, okay, here there's hunger, but 150 kilometers that way, or maybe 300 kilometers that way, there's a good harvest this year, because it's very rare that a whole continent fails. Yeah? So if you're in Sudan, maybe northern Nigeria has a wonderful harvest. Well, why don't you buy your food aid there and move it 300 kilometers northwest? So northeast in this case. So for local food aid would be an interesting one. People have been talking about it a long time, so it's not just technical why people don't do that. Yeah, there's all kinds of good and not so good reasons why people don't do local food aid. Biofuels, it's already starting to go down a little bit, but you know, still people, you know, before we have a smart alternative for, let's say, jet fuel, biofuel might be a good one. And this is Jatropha, for example. You can make diesel out of it. It's very interesting, but where are we going to plant it? How much do we need? What are good niches? Where are the places you can grow it? Well, a system like this may be able to tell you something. Traditional grains. We have in the West, we have a lot of problems with the people cannot stand gluten in their food. So wheat and stuff like that is problematic. All the traditional grains of Africa, like sorghum, they don't have gluten in it. So it's interesting. Yeah? And what's happening now is they take the grains out of Africa and they grow them in the US, they grow them in Australia. But maybe it would make sense to also grow them there and have, operate on the international market. Higher value crops, so it might be interesting. So like, for example, the cotton harvest of Burkina Faso, big companies like Levi's and stuff like that, they come in and before the harvest is there, before actually the first seeds are in the ground, they buy the cotton harvest of eastern Burkina Faso. And it's an auction and stuff like that, and they buy it. So if they might want to know during the season how their crop is doing. That's worth a lot of money, because if it's doing well, they're fine. They say, okay. But if the crop is not doing so well, they have to find some alternatives. And the same for cocoa, tea, coffee. So there might be a lot of interesting, a good knowledge of what's happening on the ground might be very valuable. A nice one which came up actually just a few years ago is insurance. With all these droughts and stuff like this, we might not have crop insurance. In many countries you have crop insurance. Why not in Africa? And there's a couple of initiatives. For example, Kilimo Salama one by the Syngenta Foundation. And what here you see basically the scheme. So you buy the inputs. That's why Syngenta is interested in this whole scheme. It's not all just because they have such warm hearts, but okay, it doesn't matter. You buy your inputs. With the inputs, you pay a little bit extra for insurance. You get your thing. In the meantime, during their season, they measure the weather. And you see what they measure it with. And these are the traditional ones. And you see this is a wind meter and things like that. These are very difficult to maintain. And we've been running projects in Africa for many years, and we always have problems with stations like this. We don't even start with it anymore. Anyway, if it goes wrong, they get compensated. And how do they get compensated? They get compensated with a little phone payment that we talked about before. So it's a very simple scheme, a very robust scheme, and they are now already covering 50,000 farmers. And so it's something that scales very well, but they would like to have better stations, better information on what's going on. Yeah? And it's worth something. And we don't need an awful lot of money. We're not in it to make money off of the whole system anyway. It just should, be paying for itself. Other things, hydropower, irrigation, drinking water. Okay, let me then come to the part that I hope you will tell me something about, with the education part. Because we were thinking, okay, we would like to put these stations at schools, at high schools, junior high schools, for example. And we would like to develop a curriculum so it fits in there. And we had a first pilot of a science communication student. And she went to 2 schools in Ghana, 2 junior high schools. And she started talking with the teachers and say, well, how can we, she brought 2 of these simple weather stations just for the trial, and say, okay, what can we do? And it was, I mean, I should say it was a wonderful success, and it was very easy, and everybody was into it. It was not completely like that, of course, but there was sufficient positive feedback to say, okay, yeah, there might be something in there. An alternative way is, well, forget about these schools because you have children there, and children have little fingers and they do things. We don't want that at all. Just put the big fence around it. Put, for example, the telecommunication people, they have masts all over Africa. They have power there. There's a big fence. People understand what it's doing. Why don't you just put them there and forget about it? We still think that trying to have this educational outreach will actually increase the social benefit of this whole project. Plus, we think that it's actually, in the end, it will work. But of course, it demands extra work, and we need we have some people who know about it, but we're not experts on education. So I'm very curious to see what you have to say. We had a nice little pilot, like I said. She made this poster, and then, they made whole storylines according to the, very much in accordance with Ashanti mythology and stuff like that. All these stories they always tell there, very much like it. And this is this little guy who makes then these little weather stations. It's called Anansa for some reason. Anyway, he goes through all kinds of adventures of making and running these weather stations. So it's possible to include it, but it's still quite a path. Now there's another project. I mean, have you ever heard of this project? Mm-hmm. It's still going on. So at some point they say, oh, it was a complete failure. It was interesting to see that they used exactly the same design principles, but it's going now in Rwanda and in Ethiopia. And so maybe that would be an interesting way. Just piggyback on the rollout of this project, see how that's going, and then once there's sort of like a network or an internet even connection, it might be easier to have this station out there and then have the data on your computer and see with it, play with it, understand it. So yes, we need to develop this educational package and teach children about their environment, and also what I think would be very nice, you know, it's not just taking out the data and then, you know, you never see them again. Now it should also be, you know, these data should be interpreted, should come back, and so you start understanding, it's like, okay, what's happening here has something to do with what's happening there, and how they're all connected through System Earth, if you want. So that's what we hope to do. The next step, actually this summer we'll go and do some more field testing, but we hope actually to organize some of this crowdsourcing. And in here we have a lot of these crowdsourcing things. All the students, there's competitions all over the place. I have not seen them much in Africa, so we're trying to do that, to organize that, have some kind of competition, and then maybe have the top teams meet or something like that. If you're still around on Friday, I'm not sure, many people are leaving, but if you're still around and say, hey, what am I going to do on Friday afternoon waiting for my airplane, we have a little meeting where we try to get sort of an organizational meeting. So yeah, I'm interested, I would like to do something, or I can contribute something about the educational package. Please come see us in Splinter Meeting Room number 5 in the afternoon on Friday. That was my story, and I hope you will have not just questions, but also especially suggestions for me. Thank you very much.